So here's what you're going to need for the videos in this section. Newton's three laws govern the dynamics or the motion of objects. The first one says that it takes a force to change the motion of an object. It One aspect of it is that if you have an object at rest, it will remain at rest unless there's a force acting on it. So that's the pretty obvious, trivial aspect of it. There's one less obvious aspect of this law is that if an object is moving at a constant velocity, it will remain moving with that velocity unless a force acts on it. So this is a little bit less intuitive for most of us here, since that goes directly against our experience on Earth. You can say, well, why do I need to keep the gas pedal pressed in my car? Why can't I just like speed up to 65 miles an hour on the freeway and let my car cruise? The fact of the matter is that on the surface of the Earth we have our Earth's atmosphere. We have a lot of friction, air resistance, and generally plenty of forces out there to act and to change the motion of an object. So because of that, it always feels somewhat counterintuitive to us. But remember, if you were to take your car somewhere in outer space, if you accelerate up to a certain velocity, and then you will not need to maintain that velocity, it will stay there on its own. So anyway, second law is where we usually the second law is what we usually use to write down our equations here in dynamics. We don't have ready-made equations, so the whole trick here and the art and the technique will be to learn how to write down our equations for each problem in the dynamics sections. So the net force, the second law says that the net force on an object is directly proportional to its mass. So this is the law that we usually write down as F is equal to ma. Here I've wrote it in a vector form, in the most proper way to say that the sum of all forces, which we call the net force, will be equal to the mass times the acceleration. In the examples later, you will see that we never use this formula directly, but we like to write it in its components form for the x and the y components. And we'll have the third law that is the action and reaction principle. The easiest one, it's easier to actually illustrate what that principle is here. So imagine you have some rectangular object and then a little ball touches it. The action and reaction principle says that if the ball exerts a force on that rectangular object, let me call that force F1 to the right, then the rectangular object will react and exert a force equal in magnitude but opposite in direction. So this will be F2 on the little ball. This is also I have to emphasize here that these two forces, when you draw the vectors for them, they always have to be applied at the contact surface. Otherwise, they would not. It will not work unless it's gravity, but we'll get to that later. The way we write this action-reaction principle, or Newton's third law, is simply to say F1 is equal to minus F2 when it comes to when they stand for the same one and the same interaction between two objects. Now let's look at the forces that we're going to see here in the next section. We're going to start with gravity, or actually with the universal law of gravitation, which is the only force that you're going to see that acts over distance. The Earth exerts gravity on the moon, and the moon exerts gravity on Earth. But even though they don't really are they're not really in physical contact. So this is the one force that you're going to see acting over distance, and it's always attraction as far as we know. Nobody has ever found any gravitational interaction that shows up in any form but attraction. In other words, it pulls objects towards each other. So let's imagine we have here a little tiny spherical ball with a mass m1 and then another one with a mass m2. If their centers are at a distance r from each other, the default distances are always measured from center of an object to a center of an object. So the universal law of gravitation will tell us that the magnitude of the gravitational force is going to be equal to this constant g, capital G, times the product of the two masses, m1, m2, divided by the square of the distance between the two objects. The capital G here is the universal gravitational constant, and its value is 6.67 10 to the minus 11 Newton times meter squared divided by kilogram squared. Again, remember the force, the direction of the gravitational force is always inward along the connecting line. Now let's see how that universal law of gravitation plays out on Earth. In 99% of the problems that you're going to solve, the situation will be about an object on the surface of the Earth. So we will still have the law applicable. That's why it's called universal law of gravitation. This law applies for any situation as far as we know in physics. So we are going to have that universal law of gravitation. But let's look at what happened when I recognized that on the surface of the Earth, there's only one object that is large enough to have a significant gravitational force, and that's our Earth itself. So you don't have to worry about the gravitational pull between two chairs or between you and your friend. It will always be between the only time that you need to consider the gravitational force will be between a given object and the Earth. So in that context, the first mass of the two objects will be the variable here. Maybe you have a car, or maybe a little ball, or maybe a chair, whatever you're working in that situation. And the rest will actually will be either constant or something that is fixed for our Earth. So that's why I rearranged these terms here. You can see I moved one of the masses, m1, and I called it the mass of the object. And then that has to multiply the rest of the expression, which includes the universal gravitational constant, the second mass, the m2, which I called it the mass of the Earth, divided by the distance squared. But here's the surprise, the pleasant surprise. So for any situations where you're dealing with objects on the surface of the Earth, the distance between the object and the center of the Earth is approximately, or for all practical purposes, equal to the radius of the Earth. Don't worry if this is a building and your object is on the 10th floor. It could be on the 100th floor, it could be in a skyscraper. You need to lift an object maybe in the 100 kilometers or above the Earth for you to see differences. So in short, anytime when you're working with day-to-day situations, unless it's a rocket and you're about to launch it off the surface of the Earth, you can take this distance between the object and the center of the Earth simply equal to the radius of the Earth. And something very interesting happens here too, again, because when I replace the constants and the value for the mass of the Earth and the radius of the Earth with what we know, it turns out that the gravitational force will be equal to the mass of the object multiplied by this expression, which turns out to have a numeric value of 9.8 meters per second squared. That is not really a coincidence. It's a beautiful testimony of how of our understanding of gravity and how things move. This is indeed G, what we have been calling G, or the acceleration due to gravity, and the value that was actually determined by Galileo in his experiments. So to summarize, when we're working on problems from this section, we will be using the simplified expression for the gravitational force, which is F is equal to mg, and we'll consider that is always directed towards the center of the Earth. Let's look at the normal force and friction now. Those are the next forces that appear very commonly here in mechanics. They both emerge from actually the electrostatic interaction that accounts for the shape and the objects. But electricity is a topic of physics too, and so we don't need to go there and get bogged down into all the details. For the purpose of mechanics, we don't need to go deep and understand what exactly fundamental interaction accounts for that normal force and friction. We can just look at it and approach them from an observational standpoint. So what we see and what we call the normal force is a force that usually always reacts actually against an external push. And it's always away from the contact in a perpendicular direction to the contact surface. Let me show you a couple of examples to illustrate what I mean by that. So the most common scenario you're going to see is a box placed on the ground or on a table or some horizontal surface. And even in the absence of any other forces, we have gravity, and gravity pushes the box against that support or table or ground. And so that support, ground, table will react, and that reaction will be directly up, perpendicular to the contact surface, and we'll call it the normal force. This happens in easily 95%, if not 99% of the problems, to a point where a lot of times students forget that the normal force doesn't the normal force doesn't have to be up. Here's an example. What if you place a box or against the wall? So normally you'll see that the gravitational force is actually down, and any reaction to it will be up, which is not really perpendicular to the surface. In other words, the gravitational force does not really press the box against the wall. Someone else has to press that box against the wall, and the moment you press that box against the wall will react. And so the reaction here will show up once again away from the interaction of the objects from the contact, perpendicular to the contact surface. You will see there's actually one example in the section of a problem where a book is pressed against the ceiling. And this is a situation where actually gravity, if anything, is pulling away. So it's not responsible for that contact of the book against the ceiling. But we have someone else pushing up and to the right. And so because of that force, we can see actually the reaction of the ceiling is downward. So I wanted to show you this example so to remind you that the normal force can be in any direction. The important thing here for the normal force is that it will always be perpendicular to the contact surface, and it always will point away, so that to oppose that pressure of the box against the surface. So what about frictional force? Well, the frictional force also reacts, only it reacts against an attempt for sliding. So its direction is actually always opposite, or preventing a sliding, and it's parallel to the contact surface. So here's the example. If we go back to that example A with the box on the surface, a horizontal surface or a table, and we have gravity down, we noticed that normal force will be the reaction of the table up to prevent, to push against the gravity. So there's no call here for friction at all. But if there's an extra force pushing or pulling that block up and to the right, they will be sliding across the surface, and then there will be a reaction from that surface. We will call that reaction frictional force. It will draw the vector to the left, opposing the sliding. If we have the block against the wall, here you can see the gravity actually naturally will drag the block or the book or whatever you have to slide against the wall. And so here the reaction of the wall will be accounted by a vector parallel to the contact surface, and we will call that the frictional force. The frictional force, there are two different scenarios here when it comes to the frictional force. The first scenario is when we actually have a sliding, or the sliding is present there, and we talk about kinetic friction. So when we have kinetic friction, the magnitude of the kinetic friction is always a fraction of the magnitude of the normal force. How much that fraction is determined by mu here, that I have marked as mu k, and it's called the kinetic coefficient of friction. If there is no sliding, we talk about static friction or traction. And things could be quite tricky, because if there are no forces to react, or no forces trying to push the object to slide, if there's no need for reaction, there might not be friction. Or if there are forces, there will be friction. So we see that for the static friction, we can have the magnitude of that friction anywhere between 0, when there's no need for reaction, and some maximum value, which once again is equal to a fraction of the normal force. This fraction is determined by the static coefficient of friction, which I have marked as mu s here. Generally speaking, the two coefficients of frictions are close to each other, but not necessarily equal, even if you have the same type of surfaces touching each other.